return to the world's fastest on Modern Marvels. In Shanghai, China, it's opening day for a train line unlike any other on Earth. Almost silently, the streamlined coaches begin their journey. Soon they're traveling at a very untrain-like speed, a blistering 270 miles per hour.
We actually like to think of our train as an airplane without wheels. We're flying on the ground, so to speak.
A remarkable propulsion system has started a revolution in rail travel. Magnetic levitation, or simply, maglev.
Magnets, when opposite poles are put together, will tend to propel themselves away from each other. Now, take that technology and apply it in a controlled manner to a rail vehicle, and there's incredible speeds that can be attained.
The Shanghai maglev system was developed by the Berlin-based company Transrapid. Here, in rural Emsland, Germany, Transrapid's test facility features a 12-mile track that treats paying passengers with speeds nearing 275 miles per hour.
Maglev actually goes back a long ways. The first patents were produced in the mid-30s, but it took a long time before the rest of the technology actually caught up with it. Transrapid began the R&D on magnetic levitation in the late 60s. And during the 1970s, we went through a series of test vehicles to prove the concept, prove the technology.
The technology behind magnetic levitation is both remarkably high-tech and deceptively simple.
Maglev works by taking electromagnets and using them to lift a train up from underneath and guide it down a track. The train itself rides on an electromagnetic field. To support the train, we have what we call support magnets. We have an iron core, and then we have aluminum ribbon-type coils wrapped around it. And then also integrated into that is what we call a linear generator, which is a special piece of equipment we use to transfer energy from the guideway up into the train as it's going along. Each of the magnets also has an epoxy case around it, which makes it impervious to the environment.
The support magnets are clustered together underneath the train cars.
This is a Transrapid electromagnet for levitation. It has 12 coils. Each train section has about 16 levitation magnets that lift the vehicle up. A train with 3 sections has 560 of these coils.
There's about half that number that are guiding the train, and they're located on the right and left sides of the train, and they guide it as it moves down the track.
Thus, maglev trains have no use for rails or even wheels. There is also no true locomotive.
In contrast to traditional trains, our motor is in the guideway itself. The train levitates, but otherwise it's passive.
Inside the guideway is what is termed a long stator linear motor. Similar in principle to a conventional rotating electric motor, here the stator, or windings, have been laid flat along the underside of the guideway. Instead of a conventional motor's rotating electromagnetic wave, a traveling wave is sent down the length of the windings. This attracts the support magnets on the train and pulls it down the guideway.
It's like a surfer stands on his surfboard. If the wave goes faster, the surfer goes faster. If the wave slows down, the surfer slows down. We're doing the same thing with electronics.
Perhaps most remarkably, there is no onboard operator.
The Transrapid is essentially the world's largest radio-controlled train. We have no driver. We have a control room, and so the whole system is run using very sophisticated computers.
We can see where the train is at all times. Control its speed from right here in the control room. All function of the train can be monitored from right here.
The control room uses radio signals to constantly monitor and manage the progress of the train. The guideway itself is controlled in the very same fashion.
The motor in our train is actually in the guideway. and we power that motor from substations which are located along the route. And we feed that power out through cables up to the guideway, but we actually send it to the guideway at about half-mile increments. And we turn each half-mile on as the train goes by. And so as the train is moving down the track, we're actually switching the guideway on and off as the train moves down.
But far from the test track in Germany, the Shanghai maglev turned heads, and not only for its record-breaking speed. Its massive construction was also remarkably rapid.
The Shanghai project was phenomenal. The total project took less than 3 years, from signing of contracts to the opening day, which is a record in itself.
Running 20 miles from the city's financial center to the airport, it has already proven the speed and reliability of maglev technology. The train runs on time and is rarely out of service.
After about a year and a half of operation, the train is actually running better than we all thought. We're currently running at about a 99.6% uptime.
120 more miles of guideway is already being planned to the seaport city of Hangzhou. This addition alone is nearly 10 times longer than the very first railroad tracks laid in the United States nearly 2 centuries ago.
Rail travel really came into being in the mid-1820s. The Baltimore and Ohio Railroad became the nation's first common carrier. Their first segment of track was about 13 miles.
Using primitive wood-burning engines, these early trains could attain speeds near 20 miles per hour. The American Civil War would provide the next great leap in train speed and technology.
Speeds were increasing. You saw trains moving up to 40 miles an hour, and the technology had moved to a boiler that now was oriented horizontally, allowing the greater speeds.
By the turn of the 20th century, steam engine technology had been supercharged. By burning a hotter fuel, coal, these engines could attain even greater velocities.
They're trying to draw as much power out of the steel wheel on the steel rail as they possibly can, and there's some marvelous technology that's being developed during this period.
One visual innovation of the first decades of the 20th century was the curb appeal of these newly streamlined engines.
The Pennsylvania Railroad GG1 electric locomotive was developed in the 1930s, very capable of speeds over 100 miles an hour. This train was a beautiful maroon streak traveling across the Jersey and Pennsylvania countryside.
The Second World War would mark the end of the railroad's golden age. For after the war, passenger traffic plummeted.
It was because automobiles and airlines offered freedom combined with speed. And in the 50s and 60s, you saw some interesting last gasps of railroads attempting to push technology for speed. One of those is the General Motors Aerotrain. Using diesel technology, General Motors developed a train that was capable of traveling 102 miles an hour. Unfortunately, there were some technological flaws with the train, and it didn't take off and garner the curb appeal that they wanted.
Beginning in the 1960s, some countries started to offer higher speeds by placing new drive systems on the standard rails.
And some prime examples of this are things like the Japanese bullet trains, an electric-powered train running steel wheel on steel rail, yet attaining speeds over 186 miles an hour.
Another design, the French TGV, or Train à Grande Vitesse, is a wholly integrated system with updated track and switching technology. It set the old rail speed record of 236 miles per hour, which stood until the Shanghai maglev smashed it by over 30 miles an hour. And when will the United States get its chance to join the maglev club?
In the U.S., actually, we're pursuing 5 or more projects at the moment. The furthest advanced are in Pittsburgh and in Las Vegas. And the Las Vegas project eventually will go all the way to Los Angeles. But we're currently waiting for the Congress to pass the next all-encompassing infrastructure law, and we're hoping the construction money will be in that law for the first maglev project in the United States.
While the speed record set in Shanghai may see challengers in the near future, another, far more dangerous world's fastest